First, I just want to make sure I give credit to the people who did a lot of the work on the testing and for the content for the presentation. So my colleagues, Roy Kaiser and Peter Kopp, certainly contributed a lot to the presentation, and I want to make sure that they get recognized as well. So first of all, quick overview of who we are, Excelitas Technologies. We are a photonics company. We have a lot of different photonics technology, whether that's in lighting, optics. We have a large and growing portfolio of UV curing brands, including the Omnicure brand, which is where I come from. And recently, Phosion and Nobolite as well are now part of the Excelitas Technologies company. We have locations globally. We have service and support globally. So it's a large company, many different applications that we work in. But custom photonic solutions is really the main part of what the company does, and that fits in very well with the UV curing business. We have over 7,500 employees, and we are currently privately owned by AEA investors. I'll just give a quick overview of the timeline for the company. So from Omnicure Technologies, we joined Excelitas in 2013. At the time, we were Lumen Dynamics. And then certainly the recent acquisitions, 2023, we acquired Phosion Technologies, and then 2024, Nobolite Technologies, so certainly growing our stable of UV curing technology. So when we talk about the UV curing process, right, we're talking about curing of inks, coatings, adhesives, where we use as a photoinitiator. If sufficient light of the correct wavelength is absorbed by the photoinitiator, begins the curing process. If it receives enough energy, you get to a final turning the liquid into a solid, and the way in which that is cured will affect the physical properties, and that's the key. When you're doing a curing process, you're changing a liquid to a solid, and that solid piece that you end up with is going to be what you have in your process, and it's very key that you're able to get the physical properties that you need and get those repeatably achieved every time you have your process. And for that, you need to be able to control your curing process. And the technology required for that is multiple different technologies. Obviously, you need to generate the light, and whether that light is a lamp, an LED, a laser, you need to be able to generate it in a consistent way. Often optics are used. We use many different optics in our systems, and whether those optics are lenses, filters, reflectors, it's the way in which you project the light, whether you optimize how the light hits the substrate, and again, has to be the same each time. You need to be able to control the light, and very importantly, you need to be able to measure the light. Radiometry is a key on any process. If you can't measure it, you can't keep it as a repeatable process. So radiometry is key. And then the last one there, well, as an equipment company, we're not experts in the photochemistry. We cannot design our equipment in isolation. In order to have a successful process, you need to work with the formulators, and that's very important, and especially important in some of the things where I'll talk about where people are looking to maybe convert from a lamp technology to an LED. It's really important that you work with the formulators because, as I said, the chemistry will react differently to different light sources, and if you're not working together, you're going to have problems. Talking about the benefits of UV curing, again, most people here I'm sure are very familiar. You get things like instant cure, reduced cure times, you can increase productivity. You can control the cure because, again, you can control the light being generated, the light being shining on your parts. Energy savings compared to a number of different curing technologies. You can have some energy savings. There's different single component coatings, which makes life easier. You're not mixing different two parts, epoxies. And so there's lots of different benefits. Environmental is one. I'm going to touch on that one a little bit more because that is something that we have always talked about as UV curing industry, and the benefits of reduced VOCs is something that is really a benefit of customers changing from different technologies to UV curing. But when we talk about moving to LED systems, we see even more benefits. And some of that is low temperature curing. So I'll get into more details, but particularly if you're doing parts like plastic parts, thin films, where heat can be an issue, heat can cause problems with the final curing, LED has some benefits so that it can help you maintain lower temperatures. Lower running costs, obviously, something people are always looking at. The LEDs just certainly have a lot lower power consumption and can certainly help to save on lower running costs. They also have very long lifetimes, 20,000 hours, 30,000 hours, 40,000 hours. Really the technology with a well-designed system, you can get very long lifetimes to the point where the system often outlasts the process that it's being worked on and is just replaced when the process is being replaced. They're also easily integrated. Typically the systems are all fully sustained. They have the cooling mechanisms within the system. They can be easily integrated into an automated system. And because there's no venting required, again, it makes it a little bit easier to put that in some sort of automated process. One of the areas we're starting to see a bigger push is on the environmental area. And as I said, this has always been an area where Radtech has promoted the fact that UV curing is environmentally friendly. We use fewer VOCs in our process, but that's typically talking about the material being used. In this case, we're now starting to talk about the equipment and the LEDs being more environmental friendly. And in most cases, the green aspect of a process that really drives the customers to make decisions is money. And with the LEDs, the costs are lower, there's lower running costs, but we're starting to see customers, and not only our customers, but our customers' customers start to push them into processes that are more environmentally friendly. And we're starting to see that flow back where they're starting to look at LED technology as an option for some of the processes where they may be using a mercury lamp. So with the LEDs, there is no mercury. There's no ozone generation. It's a lot less power. We certainly, again, we see this from a cost reduction, and during the COVID times when we saw energy prices spike up, we started to get lots of phone calls of people very interested in the cost savings of energy reduction moving to LEDs. And there's no consumables, so there's no lamp replacements, you're not replacing reflectors, you're not replacing different parts. So again, LED just takes it one step further, and we are more and more seeing customers look at those benefits and not just the cost benefits. When we look at the different curing applications and things that we have seen move from lamps to LED, it's a wide range, lots of different areas looking at it. Anytime any of these applications move, as I said before, it's not just the equipment, it's the formulations. And the formulations have to be there in order for those applications to look at moving to LED technology. We've seen it in medical, not as much. Medical are much more reserved in making any changes, but we're starting to see it. New processes, our medical customers are looking at LED. Optical fiber, wood coatings. Again, as the formulations become available that work with the LEDs, the customers are starting to move there. Wire and cable, automotive, again, printing's on different applications of printing, well established in places like digital printing and starting to become more established in other areas as well. The other part we have to keep in mind is the radiometry. And one of the challenges we saw early on as customers were starting to transition to LED was they were trying to use the same radiometer they used with their mercury lamps and measure the LED output. And that just doesn't work. And so that was a challenge early on. And even though the LEDs will degrade at a slower rate than the lamps, there's still degradation. You still need to be able to monitor the output and be able to control that. And so radiometry is still key. The good news is the radiometry has improved significantly since the early days of LED. There's lots of available radiometry that works specifically for the LED technology. They have to take into account the narrow spectral distribution of the LEDs versus the lamps. So please do not use your lamp radiometry for LED. There is lots of good equipment available for you to use that will be accurate. When we are looking at the curing process, the different light factors that will control that process, the irradiance level, the exposure, the combination of the two, going to give you your dose, the spectral content, and that's really the key one that I'm going to talk about in the next few slides on the spectral content and how it changes between a lamp and an LED, and then things like the heat that's generated from the process. And the way that the combination of these light factors come together in your curing process will affect the final properties of your cured material. So when one of these changes, such as the spectral content, as that changes, the properties of your cured material will change. So this is a chart. I apologize, this is an old chart, but it does show the difference in the spectral distribution between the LEDs and the lamps. These days, the actual output of the LEDs is really sufficient for most applications. We have equipment now where you're getting over 20 watts per square centimeter of irradiance from 395, 385 LEDs. The power's there, but it's the spectral distributions that is very different. You can see in that chart. This is one of our mercury lamps. Goes from about 250 nanometers to about 500 nanometers, although we have a filter in there to eliminate the IR element. But you can see in the lamp, the distribution, you have about 40% UVV, 40% UVA, and you have a bit of UVC in there. The LEDs, it's all, if you're in the 405 nanometer, it's all UVV, 365 is all UVA. There is no distribution throughout the spectrum. So it's a very different distribution. And when we talk about the curing requirements, obviously the effective irradiance talks about the irradiance within a specific wavelength that's used and absorbed by the photoinitiator for curing. If you don't match the requirements of the photoinitiator with the output of the light source, you're not going to get curing. And so for that, we do offer multiple wavelengths of LED, 365, 385, 405. Try to help match as much as you can. Because it is a very narrow, you have to be very sure that you're matching what's required on the photoinitiator. Now, I talked about lower heat, and that's one of the keys because with the broadband, there's light being absorbed by the photoinitiator for the cure, but you're also having light being absorbed by the different components of the adhesive. You're having light being absorbed by the different parts that are being cured together, and you're having light that can, that light as it's being absorbed can generate heat. So the narrow spectrum of the LED can help to minimize that heat. If you're targeting just what's required by the adhesive, if you're looking at the parts that you're curing and you're making sure that the light is not being absorbed by those parts, again, you can minimize the heat. And this chart here is just an example on where full spectrum, you get a certain amount of heat. Added a cooling filter, eliminating the IR spectrum of the light, you can reduce the heat. But with an LED, where you're targeting just what the adhesive is absorbing, the parts are not absorbing light, you can really start to minimize the heat. So, important to select the right wavelength. Certainly starting out many formulations, many people were looking at 365 nanometers because that's what they were used to, the large peak on the mercury lamps. That's what they were looking at. We have seen over the years many cationic photoinitiators. 365 is very well suited for that. Some of those do not go up above 380 nanometers. Many of the free radicals, though, will go well above 400 nanometers. And so early days, we saw a lot of success with 395 nanometer LEDs, and today still. Today, I would say, on our LED systems, it's still generally about 2 to 1 that we sell more 395 than 365, even though many people would often come to us and saying we need 365 because that's to replace my mercury lamp. But different wavelengths will work. Again, you have to work with the formulators, work with the chemistry, and find what works. One of the challenges, though, that still remains with the LEDs is surface cure. And that's something has been there for years. I've talked about it in different presentations about the oxygen inhibition. And one of the areas we're seeing improvements is the use of UVC LEDs. And I know, again, people have talked about it here at the show, and using the combination of UVA and UVC LEDs to improve the surface cure. So from there, I'm going to talk about an actual application where we looked at that. And what we were doing is we were working with a customer. They were curing alkoxy silicones. It was used in a gasketing application, and as is fairly typical, this was a dual cure adhesive. So the initial cure for functional strength was done with UV curing. In this case, it was using a mercury lamp. And then a secondary cure over time was done in a moisture-rich environment. And that could take up to 24, 72 hours. And the combination of those two produced a very good part. And the process was working very well with the mercury lamp. They didn't need to change it. This is a case, though, again, where their customer came to them and said, we would like to look at and investigate moving to LED. We want to see it move to a lower energy process. The customer obviously was interested. They wanted to look at lowering their energy costs, also reduce consumable costs, and lower the infrastructure. Again, there's no ozone, so there was no venting required. So we worked with the customer, did some testing, and as we have often seen over the years, simply replacing a mercury lamp with an LED presents some challenges and presents some things unexpected, things that were not happening in their process previously. And in this case, what happens in the process is they do their initial cure with the UV, and then the parts need to be moved because they need to be stored or for the 24 hours of the moisture cure. In this case, with just the UVA, the silicone was soft after the first step. And so what happened was, as the parts were being moved from stage 1 to stage 2, there was material transfer. It was uneven after the curing. There was deformation of the gasket. Material was ending up on some of the operator's hands, and it just wasn't working well. So where to go from there? Oh, sorry, I'll give you a quick overview of the steps we took in the process. So in this case, we used a 365 nanometer UV system, a peak irradiance of 2.5 watts per centimeter squared at 25 millimeter working distance, and a total joules of 7645 millijoules. So energy-wise, there was plenty of energy to do the cure. Unfortunately, immediately after curing, the surface was tacky, and there was wet transfer of the materials, as I talked about. Now, the good news is after 24 hours, after the moisture cure, it was fine. The material was fine, and it got to the properties required. But the process wasn't good. It was not going to be a repeatable process if there was material transfer from step 1 to step 2. As I talked about, surface cure, that's a known issue with UV LEDs. So we had a number of options we could use in terms of what the solution was going to be. Option number 1 was do nothing. If we let the parts sit there for long enough, the moisture cure takes over and they get the physical properties. Unfortunately for the customer, that wouldn't have been so good. That would have really put a dent in their productivity if they were leaving the parts in step 1 for a number of hours. So that wasn't really a good option for them. Another option, and one we see quite often, particularly with smaller parts, I'll say, is to introduce a nitrogen blanket. And that eliminates oxygen inhibition and allows for a much better surface cure. So that was a viable option for the customer, but now you're starting to introduce increased complexity to the process. Right now you have to have nitrogen. You have to have that controlled. And it starts to add cost too. Nitrogen is not inexpensive, so if you're doing a running process, you're running through nitrogen. So again, what's driving them is cost savings for switching to LED. If we're now introducing the increased cost of nitrogen, it's not as attractive a change for them. And so the third option was trying to use a combination of UVA and then as a secondary curing step, adding UVCs. Now they had some concerns there as well, because certainly I think people who are aware of UVC LEDs there's some concern with the cost and the reliability of them. So that was something we had to work through with the customer. Ultimately, that was the solution we chose to move forward with testing, a combination of 365 and 275 nanometer LEDs. We talked about the cost. Well, I'll say the good news is the cost of the UVC LEDs has dropped fairly significantly over the years. I think I've been talking about UVC LEDs for about 7 or 8 years now in terms of the benefits they provide, and over that time the cost has dropped by about 50%. Still well more expensive than the UVAs. I'll say our UVC systems are generally at least 2 to 2.5 times more expensive than the equivalent UVA. So cost has dropped significantly, but it's still an expensive system. Lifetimes have also increased. So we used to talk about lifetimes of about 5,000 hours for L70. We're now up to 10,000 hours. So again, doubled the lifetime. So the reliability is getting better. And the testing is relatively easy to do. We're able to pretty quickly introduce a testing process that would see whether the addition of UVC helped. So what we did is we kept the UVA curing steps the same. So still 2.5 watts per centimeter squared, 7.6 joules per centimeter squared dose of the UVA. And we added in 275 nanometer LED secondary curing step. In this case, we used a peak irradiance of 900 milliwatts per centimeter squared. Now we kept that at about 70% of the maximum output of the system because it's going to degrade over time. And so in order to achieve that 10,000 hours that they talk about, we couldn't start at 100%. So we started at about 70% and gave it a dose of about 4,000 millijoules per centimeter squared. The good news is that immediately after curing, it was a much better physical properties. There was no wet material transfer. And then after 24 hours of curing, we had a smooth surface. So in this case, the combination of the two actually brought us back to their original process where they were getting very good results. So when we look at that, we see the benefits of combining the UVA and UVC LEDs. We were still able to significantly reduce the energy costs. The combination of the two different systems was still much lower energy than what was being used on the Mercury system. It still eliminates consumables. We didn't need to add the nitrogen blanket. That was one of the options we looked at, but that was not required. And still the infrastructure, again, no ozone, no venting is required for this solution. So in terms of the process efficiency, the curing time remained the same. With two systems, they had a longer curing distance that the parts had to travel through to get the curing, but they could maintain the same process time. So their productivity stayed the same. It was all done in one pass, and actually by using larger areas, they were able to do multiple parts in one time. And that was, again, just an example of a successful testing where between the equipment and the formulators, we were able to work with the customer and provide a solution where they were transitioning from lamp to LED, and worked out well in this case.